Okay, we're going to start talking about nonlinear ordinary differential equations. We're going to start with a simple first order single nonlinear ordinary differential equation. And the first thing we're going to do is linearize it. So maybe it's not as generally nonlinear as possible, but we're going to talk about a few examples anyway by drawing what's called the phase diagram or the phase space of this equation. And the key thing to notice will be that we're not trying like we did in the previous ordinary differential equations with constant coefficients and linear, where we had a solution to rely on or a guess and check solution that we could tune into space. We're instead going to try and map the characteristics of the solution, because as we discussed in class, what we'd really do in the modern era is we would code up this nonlinear model and solve it on a computer. But before we do that, we actually should know a little bit about the characteristics of the nonlinear system. How many fixed points or steady state solutions does it have? How sensitive is it to choices of different initial conditions? Maybe map out where in the space of the function the different initial conditions might be important. And so that's where the phase space diagrams can really help us. And we've already learned a lot of the tools that we're going to need to do this. So one thing, a notational thing that makes our life a lot easier, is to put a dot for the derivative. And since we know all the derivatives and ordinary differential equations are with respect to the same thing, this time I'm thinking of it as time, and I'm thinking of x as being my function that's varying with time. So x dot is just the ordinary derivative of x with respect to time. Cool. Okay, next. This is the way we had written our linear first order ODE. And remember, it was linear in x, but it could have varying coefficients that depended on the coordinate system. Cool. That's one way of thinking of things. Now we're going to think of a function of x, possibly with some other parameters. I'm just putting tau in here as an example, and I have a semicolon to distinguish the variable from these other parameters. And it's first order again, so it's just got the x dot. Okay, so what do we do if we see a system like this? Well, we want to think about the phase space, and I presumably know that function. This function conceivably could also depend on time. It could wobble around. We can think about lots of ways that it can do that. Before we get into all of that heavy stuff, let's just imagine that it doesn't depend on time explicitly. It just depends on x, but possibly in a nonlinear way. Okay, so let's draw a function. Well, we could choose a linear affine function, and we're going to be in what space? This is the space of x over here, and then in this direction it's f of x and tau, or more simply we can just say this is the x dot axis. So we have an axis which is the derivative along one axis and the function we're solving for along the other axis, which is a little bit weird. But we know that if this were true, if we were given this function and given these parameters, we could do that. We could say, give me a value x, I can evaluate that function, and then at that point x dot will be given. Okay, so let's see what it looks like for this simple straight line case. Well, the first thing you want to notice is, where does x dot go to 0? Why is that important? Well, that's a steady state solution. If x dot goes to 0, or this function goes to 0, then that means that once you get there, you would stay there. We probably are also given initial conditions that go along with this, or maybe we want to guess over a whole range of initial conditions and understand the behavior. So we'll have to get to that in a second. But for now, let's just say, where is this function equal to 0? Well, it's equal to 0 right here. That intersection at this point is where f of x given tau is, or where x dot is equal to 0. Okay, so let's think what happens if we happen to be over here and we chose an initial condition a little bit to this side of that steady state solution. Well, over here, f of x is positive, or x dot is positive, so if I chose this spot, I would be moving faster and faster away from this point. What about over here? Now I'm negative, and so I would be moving away from this point faster and faster. So it doesn't matter which initial condition I choose for x, I would be moving away from this steady state solution. And so we call that an unstable steady state solution and would indicate it with an open circle like that. And so if I start out exactly on that steady state solution, then x dot is 0 and I'd sit there. But if I was just a tiny distance to either direction, I would move away. Okay, that's the first example case. What if we just have flipped the sign the other direction? And of course, we could have solved that system. That was just a linear function. X dot equals a linear function. We already know how to solve that. We could have solved it with the guess and check method. And so we actually could have found quite easily that the rate of acceleration away from that fixed point was exponential. We would have something like e to the m times time for moving away from that, which is cool to keep in mind, even though now we're not solving these equations, we're just mapping them out. Okay, what if we have a line going the other direction? Well, we find the fixed point, this time it's here, and now if we choose our initial condition to the left of the fixed point, we're moving fast at first, and then slower, and then slower, and then slower, and then slower, hey, into the fixed point. If we start over here, we're moving in the negative x direction, so fast at first, slower, slower, slower. So this fixed point, stable, we indicate it with a filled-in dot, and so we move wherever we are to fall into that point. And now if we put on our hats and remember, oh, this is a constant coefficient case, but just with whatever, this would be a exponential decay into this fixed point. Great. That's great. So all linear systems, most of them, could be this or the other. There are a couple others that are worth thinking about before we move off of linearity and move on to nonlinearity. What if we have a linear system like this? Well, now there are no fixed points. We just move to the right everywhere we go. Cool, because everywhere x dot is positive. That's one. Or what if x dot is equal to 0 everywhere? Then everywhere is a fixed point. We don't move at all. We just don't really have a differential equation. We just have x equal x dot equals 0 at any x you choose. Okay. Nonlinear equations. So we know lots of nonlinear equations. We've thought a lot about polynomials and things. Let's just draw one like this. This is a typical, maybe a cubic function on this side. And, well, where were our fixed points? Well, we got 1, 2, 3 fixed points this time, great, because we had 3 roots to a cubic. We could have drawn a quintic and had 5 roots. We could have had imaginary roots by moving this upward so that it didn't contact. Lots of different choices here of things we could do, but let's think a little bit about what we would do if we do have these 3 roots, because the last time we had only 1 root and we always either ran away from it or fell into it. Now we might have some different behavior depending on which root we're looking at and where we start. Okay, what's happening over here? Well, x dot is positive, so we're going away, going towards larger x. Here, x dot is negative, so we're going this way. Here, x dot is positive, so we're going this way. And here, x dot is negative, so we're going this way. Okay, so here, I'm going away from my fixed point, so this is an unstable fixed point. Here, I'm going toward my fixed point. This is a stable fixed point. And here, I'm going away from my fixed point, so this is an unstable fixed point. Great. Okay, we did that much just by thinking about the orientation, and you can see that actually the slope, the local slope, is what's determining whether it's a fixed point or not. Hey, local slope, why don't we label each of these as an x star? That's x star number 1, this is x star number 2. I'm giving my fixed points a little name, x star number 3. Well, I know how to evaluate this function near a point of great interest. I can do the Taylor series. So I could evaluate this as f of x star, whichever it is, with whatever parameters might be associated with it. So this is evaluating it there, plus the x minus x star for my next term times the derivative evaluated at x star time plus the higher order terms. I don't care about the higher order terms. That's the linear function. Let's take a little closer look. Each of these is a root. And if they're a root, that means that x dot equals 0, f equals 0, which means that evaluating f of x star at any of the x stars we choose, this is equal to 0. So all we've got left is this little piece. So we have x minus x star, f prime of x star, tau. Okay. This is a constant. It might be hard to find it because we have to take a derivative of the function and evaluate it at these fixed points. It might be hard to find the fixed points in the first place. This was a really complicated function. We might have to use something like Newton's method to get the fixed points in the first place. And then we're evaluating the derivative using something at those solutions that we got out of Newton's method. And then that gives us the coefficient for this term. Let's write this out a little bit more clearly. The point I want to make is x dot x star. It doesn't have this, right now, is it a homogeneous equation? No, it's not, because x star is not, if I set x to 0, I get a 0 on this side and I get a 0 for this term, but not for this term. So it's actually really convenient at this point to define a new variable. And it's a really easy to choose one. It's just x minus x star. And on the left-hand side of the equation, I can take the dot of that whole thing, which is just d by dt of the whole thing. And why can I do that? That's equal to this side because x star is fixed in time, at least in our present conception. So if x star is fixed in time, I can take the dot of x minus x star. And that's going to be equal to x minus x star times this constant, f prime of evaluated x star and tau. Well, this is a really easy equation. Now we've got a homogeneous first order differential equation with a constant coefficient. We know how to solve this. This is just an e to the mt form. And so we're going to have it something like x minus x star equals whatever the initial value is, x0 minus x star e to the mt. Cool. All right, that's nice. Is it going to run away or is it going to fall in? Well, that has to do with whether these were stable or unstable fixed points, and that's going to determine the sign of m. M is what? Well, m is just f prime of t. So if f prime of t is positive, we're going to have a positive growth in time away from x star, unstable fixed point. If f prime of x of t is negative, we're going to have a collapse, an exponential decay into x star number 2. If we were at x star number 1, the slope is positive, m will be positive, we'll be running away. So it's unstable, goes together with a positive exponential, stable goes together with a negative exponential in time. And so that means that this key part is this parameter, the f prime of x and t, what the slope is evaluated at each of the fixed points is the key determinant of the behavior near the fixed point. This thing is called a feedback. So a positive feedback is when you say, if there's a perturbation away from my steady state, I tend to run away from it faster and faster. It doesn't matter whether it's positive or negative. Positive feedback, positive slope on the phase diagram. Negative feedback, positive exponential growth. Negative feedback is when f prime of t evaluated an x star is negative, because that means that you have a stable fixed point. So if you perturb away from it, you fall back in. Negative, all perturbations tend to decay in time, and that means that f prime of x is equal to a negative value, which means that e minus would be a negative value in time, and it would be dropping in so that x minus x star would be whatever x0 you choose, whatever initial value, this x minus x star is going to be getting smaller and smaller in time. So you're falling into the hole. Great.